All right. I am audible right now, right? Um, Hello.
Yes, sir, you're audible.
Okay. Then I'll start with the third live session. So, if we look at the problem system, they're more to do with bifurcation diagrams and Michaelis-Menten equation and so. So let's jump right into the first question. Just before going, do you have any clarifications required or doubts from the previous session, second one? You can always ask later as well. That's not an issue. Just in case I'm asking. Cool. Go ahead with the third one then. So the first question, if we see, it says for an ODE, the dx by dt equaling ax minus x square. We draw a bifurcation diagram. What are the axes, horizontal and vertical, for the diagram? So how do you draw a bifurcation diagram? You draw a bifurcation diagram for the system as the system is varying with respect to a bifurcation parameter, right? So you do not bifurcation diagram, you do not draw for state variables per se, you draw for the other parameters of the system. So for our case here, a is a parameter of the system, parameter of the system. If suppose we had two variables, let's say for example dx by dt equal to again ax minus bx square or something, then a and b both would be the bifurcation both would be parameters. How the system changes with respect to a and b would be different, but yeah, the essentially that is what a parameter would mean, right? So now, since we are considering a as a parameter of the system, we try to find the bifurcation diagram shows how a system behavior changes with respect to the bifurcation parameter. Bifurcation parameter. So here, since a is our bifurcation parameter, y-axis would be how the system behavior changes. So in our case, it's only a one variable system. So we have x on the y-axis. So suppose it was a system of ordinary differential equations. That is, we have dx by dt equal to some f of x comma y, and then dy by dt equal to some g of x comma y. Then it would be a two variable system, right? So in that case, it could be either x or y, and both could vary differently with respect to a particular bifurcation parameter, right? So in our case, since it's only a one variable system, y-axis, which would be the representation of system, is x, the state variable, and x-axis would be our bifurcation parameter. And since here we have there is only one parameter for the system, which is a, we have a. It could There could be multiple, but in our case it's only a here. So a is on the x-axis and x is on the y-axis, right? That's with the first question. Next, second question. We have two bits. So first question, they're asking us, show that the following ODEs have bifurcation. So first, dx by dt equals ax minus x square, right? So what do we require for it to have a bifurcation? That is to say, As we are changing the parameter a, the behavior of the system is changing. So we need to say that for different values of a, we need to show that for a certain change in value of a, the behavior of system changes, right? Now let's consider the steady states of the system. So for steady states, what do? We take the dx by dt equal to 0 to find out what the steady state behavioral system is. So here that would imply ax equal to x square, which would then imply either x equal to 0 or x equal to a are the solutions for this at steady state, right? And if you see here, if say a equal to 0, if a equal to 0, then x equal to 0 would be the only solution, is the only solution. If if a is greater than 0, then we need to check if what kind of stability the system has, right? And if a is since here we do not have a specific value of a, we are trying to check generally the for the general variation of a, that is to say a is negative, a is 0, and a is positive. Those are the three things we'll be checking. Of course, if there are, there's some particular fact limitations which are coming up in the equations, and then you can say like from -2 to -4 it behaves in manner, and from 5 to 10 it behaves in a manner. That is also possible. But here, since for this particular equation, since we do not have anything as such, I'm just taking a greater than 0, a less than 0, and a 0, right? Okay. Now how do we check for the stability of the system? We try to take the derivative of the whole thing with respect to whole function with respect to x, right? So if we do that, if this is, let's say, f of x, then d by dx of f of x would be a minus 2x, right? Now if a was if a was greater than 0, if a was greater than 0, then at x equal to 0, let's say let's just put this as 1. At x equal to 0, 1 is greater than 0, and at x equal to a, 1 is less than 0, right? So this would be unstable, and this would be stable, right? If you remember, we had seen this before, taking the derivative of the function given that is to say dx by dt with respect to x, if we take the derivative, and we have this a minus 2x here, and we check its sign at the particular steady state. If it's negative, it is stable, and it's positive, it's unstable, right? Now if a is less than 0, at x equal to 0, 1, what would it be? X equal to 0, it would be negative. At x equal to a, 1 is since a is negative, minus 2a, that becomes minus of 2 into minus a, so plus magnitude of 2a, so that would be greater than 0. Essentially these are switching. The stabilities of the same steady states are switching, right? If you see from these two steady states, stability of the steady states is are switching. Stability switches. So what we conclude here is that as there are variations in the bifurcation parameter A, the stability or the nature of stabilities of the system changes. So this could as such not, this is not necessarily that it is not necessary that it has to be only switching of the stabilities. It could be switching of the stabilities, vanishing of certain stabilities, or popping up of new stability states, stable states, or it could be any kind of change, right? Then that would any kind of change in the number nature of the stability of the system, that would mean there's a certain bifurcation present. Um, right, so here we see that there is a bifurcation present in for this particular OD. One has bifurcation. Let's move on to the second one right now. What is the second equation? Dx by dt equal to ax minus x cube. That's right, let me just check that. Yeah, it is ax minus x cube. Right, again for this first we find the steady states. For steady states, again we do dx by dt equal to 0, which would imply x equal to 0 and x equal to plus or minus root a, are the steady states. Okay. Also, since if we take this as f of x, then d by dx of f of x will be equal to a minus 3x square, which we'll write for now as 1, so that we can compute later. Right, so for now, for the first consideration, we have if a is greater than 0, then we have at x equal to 0, 1 is positive. At x equal to plus root a, we have 1 is a minus 3a, that will be negative. And similarly at x equal to minus root a also, it is negative. That is to say, this is unstable uh, these two are stable steady states for a greater than 0. So if a is equal to 0, then at x equal to 0, 1 is a is equal to 0, 1 is uh, equal to 0, right? So this would be an unstable system. Cool. So again here you see from a equal to 0 to a greater than 0, the stabilities are changing. That is, there is only one unstable steady state. Two, there are two new stable steady states which are there. So if let's just check if a is less than 0, then we have it complex numbers coming up, since we have a root of a negative value at x equal to 0, 1 is negative, at x equal to plus root a. Um, Plus root a whole square. So that will be minus 3 again, negative minus. So again 1 is negative. At x equal to minus root a also 1 is negative. So that means all three are unstable. Right. Again, if you see for these threes, the stabilities change. Stabilities, the nature of the stabilities of the system are changing. So 2 has bifurcation. That's how we show. Let's check what they have shown in the solutions. They've sent x are stable steady state x equal. Yeah, that's what there is. So number of possible steady states and their stabilities are changed with the value of the parameter. Therefore, the system has bifurcation. Right? Okay, that is with the second question. I'll just stop for a second. Are there any inquiries or doubts, clarifications you want to ask? Okay, in that case, I'll go to the third question. So third first bit we have two paths in this motif, 1 and 2. So we just we calculate sines along both paths and see how they are. And then here also we see that both paths, both 1 and 2 are in same direction, right? That is, both of them are reaching from no. Let's say this. Let's just name this A and B. It's going from A to B. That's what I meant by saying that they're in the same direction. And then sine of 1. So we what we do is we take as the arrows as positive and inhibitions as negative, and then we multiply along a particular path or what the final sign of the path is like. If there's arrow, we have positive times positive, which is positive. So 1 is positive and 2 is positive. Since both of them are positive and in the same direction, it is a coherent feed forward. Right, so essentially if they're in the same direction it's a feed forward back, but if there is an or they're in opposite direction, there's a signal going from A to B and then from B to A, that means it has a kind of feedback in the loop, right, in the motive. So for the second one we see um, the first path remains the same, but there is a reversal in the direction of the second path, right. That's again 1 2, 1 and 2 are in opposite directions, and 1 is positive times positive, which is positive. 2 is negative times positive, which is negative. So we have essentially a negative feedback motif. So since 1 and 2 are in opposite directions, it's a feedback, and we have the 1 and 2, the signs are opposite, which implies it's a negative feedback loop. For a feed forward, you say coherent and incoherent if they're positive or negative, and for a feedback, you say either positive or negative for the different signs, right? If we go to the third motif now, which is, so we have 1 and 2 in same direction. So this is a feed forward motif, but the signs, one is negative times positive, which would be negative, and two is positive times positive, which is positive. So it's a incoherent feed forward loop network. Incoherent feed forward. Next, next for the fourth one, we have the network given as 1 and 2 are in opposite directions. So this is a feedback loop. And 1 is positive times positive, which is positive. 2 is negative times negative, which is again positive. So we have a positive feedback motif here, right? So yeah, any doubts? I'll just stop for a second before we start with the next one. Okay, if not, let's move on to the fourth one. So here the following plot shows the function y equal to 8 times k power n by, I can see that. Let's see here, k power n by k power n plus x power n. Okay, this is how y is given. Now guess the values of a, k, and n. Right, that's what they have asked us. So let's go to the plot first. Um, so yeah, from the graph here, if you see, it's essentially a function which is falling down continuously. But if you look at the function for form they have given, that is y equal to a power k power a into k power n by k power n plus x power n. The form of Hill's function, right? So, the graph shown is not sigmoidal. Rather, it is falling down, which implies that the Hill's coefficient is less than is of the order less than 2. Okay, so that is to say, it is only n is equal to 1. Since for n greater than 1, we would observe some kind of sigmoidal behavior, though it might not be very steep step response. It is still definitely sigmoidal for n greater than 0. So if n greater than n greater than 1, I'm sorry, for n greater than 1, the function in Hill's would give sigmoidal behavior Since here we do not know sigmoidal, we do not have any sigmoidal behavior in the graph shown, implies Hill's coefficient for this particular function is 1 here. So we can directly say that n would be equal to 1, right? Now, after saying that n equal to 1, then we'll have a new equation as y equal to a into k by k plus x, right? Now we can just see what is happening at different values of x. So y at x equal to 0 would be uh, a, right? A into k by k when k would get cancelled, and that would be equal to a. So at x equal to 0, from this graph, at x equal to 0, y is equal to 4, which implies a equal to 4, right? That is the next you know, direction you can do. And then now we need what happens to the value of k, right? So for that, k is when it's kind of half saturated, right? The Hill's constant k, it is kind of where, like, if in a Hill's form, if you write, it is where the when there's a sigmoidal behavior, or for any, even for n equal to 1, where at the point where the y value goes to half of its maximum or minimal, that the difference is what is determined by the value of k, x value at which y goes to half uh, of its maximal value, right? So in that sense, what would it be? So k is half maximal, x at half maximal value of y, x at half maximal value of y. This is the nature of form of equations, be it for n equal to 1. Just that for n equal to 1, it doesn't show sigmoidal behavior. So that is then, in that case, y max we have equal to 4, right? Which is at x equal to 0. So which implies half into 4 equal to 2 is the y value. So which implies corresponding x equal to the k value, which would be at 10. If you see, this is the point where which is the half maximal value. Right, so we have 10 as value of k. So that is for the fourth. Let's just write n equal to 1, since no sigmoidal behavior. A equal to 4, substituting y of x equal to 0 equal to a from graph, then k equal to 10, that is to say uh, x at half maximal value of y. So x at y equal to 2. Again, from graph you get that k equal to 10, right? So that is with the fourth question. Let me know if you have any doubt in that. Okay, if not, I'll move on to the fifth one. So here they say the following system of ODEs is used to model gene expression under the control of an inducer I. Here, M and P are mRNA and protein, respectively, express the steady state concentration of the protein as a function of the I. Okay, so we have dm by dt equal to k1 into I power n by h power n plus I power n minus k2m, and then dp by dt equal to k3m minus k4p. So now they've asked us to write steady state concentration of protein P. P protein, the steady state concentration of the protein P in terms of as that is as a function of I. So for that, for steady state, we have dm by dt equal to 0 and dp by dt equal to 0, right? So taking dm by dt equal to 0, we have k1 I power n by h power n and plus I power n equal to k2m, which implies m would equal to k1 by k2 I power n by h power n plus I power n. Now we substitute this in the next equation. So which would be for dp by dt equal to 0, that is k3m equal to k4p, implies p would be equal to k3 by k4 into m, substituting the m we have into k1 by k2 into I power n by h power n plus I power n. So we have protein steady state protein concentration as a function of uh, I, the inducer, right? So yeah, that's quite straightforward. It's just taking steady states and then substituting in the consequent equations, right? Now we have sixth question where it says for the following reaction scheme, what are the units of K1, K2 and K3? So I'll just write down the reaction scheme here first. S and E. K1, K2 are the rates here, and for a reversible reaction, C, then K3 and product plus enzyme P plus E, right? So we have S substrate, E enzyme, C the complex in between, P product and E enzyme. We have K1, K2, K3 as certain rates. Now they're asking us to find the units of K1, K2 and K3. Okay, so first we'll write down the equations for the reaction scheme here. So let's first write down the forward and for backward rate for the first part here. So here forward rate would be k1 times s times e, right? And backward rate would be k2 times c. And similarly here there's no backward, only forward. So forward rate is equal to k3 times c. Right, now I'm trying to write down the full OD kind of equations. So I'll try to first write how the product is formed. dp by dt, the rate of formation of product, is equal to just k3 times c. Since there is only the only source of product formation is from c and there is no reverse rate for it, it's only k3c. Now if we go for dimensional analysis here, dimensional analysis here, we have LHS dimensions as uh, dp, which is again molar, we take concentration in terms of molars, m times n s inverse, that is second inverse time, right? So RHS c is again m, so which implies dimension of RHS equal to LHS, right? That's a must. Otherwise, we can't write the a physical equation representing a physical system. So we have K3 equal to second inverse. as its units, right? Not equal to, that'd be wrong. K3 as second inverse dimensions, right? Now let's write equations for the first part of the reaction. That is dc by dt is equal to k1 times s times e minus k3 into c, right? So again we are already settled with k3c dimensions being m into s inverse, that is molar times second inverse, and this is also molar times second inverse, since dc is again molar and dt is second inverse. So for this, since they are in an additive form, all of them have to satisfy the same dimensions, that is this also has to be molar second inverse. So we have s as molar, e as molar, which implies k1 goes to uh, molar inverse second inverse, right? That is the dimensions of k1. Next we write the same equation for our substrate. So we write ds by dt equal to, we have incoming from like that is formation of substrate from the complex as in the as a part of the reverse reaction. So we have k2 into c minus k1 into s into e, right? For the, as that is, since that is the forward rate. Now we have this we have settled as molar second inverse. This again is molar second inverse. This also has to be molar second inverse, right? Since c is again molar, implies k2 is second inverse. So we have k1 as molar inverse second inverse, and k2 and k3 both of them being second inverse as the dimensions. So dimensional analysis is a very good tool to actually and validate your equations, and sometimes to avoid blunders maybe. But yeah, dimensionals always have to hold for a physical equation representing any physical system, right? So from this from this dimensional analysis we can get we have the dimensions for k1, k2, and k3. Okay, now let's move on to the seventh question. So seventh question, it says for the following enzymatic reaction, uh, K1 equal to 1 unit, K2 equal to zero point 0.1 unit, K3 equal to zero point 0.4 units. If E equal 1 unit, C equal to 2 units, and S equal to 100 unit, calculate the rate of product formation. Consider the Michaelis-Menten kinetics key assumptions applied to this reaction. Okay, so if this said that Michaelis-Menten theory can be applied. So essentially, we have product formation in terms of substrate and enzyme. That is to say, when we in what do we do in the Michaelis-Menten form of equation? We consider that C is at steady state. I mean, we write it in terms of some Michaelis-Menten constant, etc., as in as a function of substrate and enzymes. But here we already know the steady state value of the complex, right? Steady state value of C is already given us 2 units. So here we do not require the even though they say it follows, we do not require the formulation to find out what the product formation rate of product formation is, since we already have the steady state value of the complex. If we do not know that, then we write it in the other form to estimate our rate of product formation. But here it's quite straightforward. dp by dt equal to k3 into c, which is a, since it is a the forward rate, and we have k3 as how many, zero point 0.4 units, right? Which implies dp by dt equal to zero point 0.4 into 2, that would be 0.8 units. Here they're just writing units to avoid doing any dimension analysis. It's assumed that they are dimensionally perfect, and that's how we are trying to solve them. Okay. Um, yeah. Next, the eighth one is heavily dependent on the particular lecture. I think it's week 3, lecture 5. Yeah. No. Yeah. Week 3, lecture 5. It is kind of the derivation is mentioned there in detail. So you will have to go through the whole derivation over there. But yeah, I will. Uh, go through the final parts of it. So I'll just write the final equations which we have, and then I'll just explain a little over that. So I'll just first read out the question. The following is a reversible enzymatic reaction where both the reactions follow the Michaelis-Menten kinetics. The K and Km are Kcat and Michaelis-Menten constants respectively. The total concentration of Y is Yt. Under which condition will the system work like an on-off switch? Right. So as in the derivation, the final representation of the system is given as here, since you have y and yp as in activated and inactivated forms, and ek and ep as the enzymes for the corresponding directions of reactions, right? So we have ek equal to 1 by k1 v2 yp, which is on the right hand side, by yt, yt by j2 plus yp by yt times j1 plus 1 minus yp by yt is yp by yt. This is the final form of the equation as derived in the lecture. Please go through the derivation once. So here yp and yt is given as the total concentration of y. So essentially y would be equal to yt minus yp at any given point, since that is a constraint put on the system, right? Now what does yp by yt represent? This represents fraction of yp, right? Fraction of yp present in system. Now let's just take this is to do with the form of equation to see how it behaves as a on off switch. Let's just take yp by yt is equal to some x, that is our variable of the system, to just to observe the function of form of the function, and ek we represent as some g. So we are writing some g of x, right? So our g of x would be 1 by k1 times v2 x by 1 plus x into um, j1 plus 1 minus x by 1 minus x, right? Now oh sorry, this is j2, right? To observe how this function looks like, I've used this. I'll just skip to this graphic calculator called Desmos, which is a free software you can use on the website. And you can, on Google you can just open and type Desmos. This will pop up. Is the graphical calculator. So here on the left side, here if you see, I've given the equation representing our form, but I've just taken the liberty of taking v2 equal to 1, j1 equal to 2, j2 equal to 4, and written the equation, right? So now I just want to show you how the system behaves, and also note that this is kind of different from the graph shown in the lecture, in the sense that I have flipped the x and y axis. You just have to flip it. But if you see here, the line passing through the origin and then saturating asymptotically at 2 points either side. That is the line we have in consideration. That is the showing the behavior of the equation. The other two kind of lie outside physical bounds. They are mathematically correct, but physically they do not make sense. So we ignore them. Right now, let's say if I put different, you can play around with values here to see how they behave. So let's say here I have instead of 2 j1 I take very less point 1, and j2 also I take point 1. That is very less values. You see that the steepness of the behavior has heavily increased. Now if I take instead of point 1 point 0 1, you see it has further increased. So as j1 and j2 the value keeps going smaller and closer to 0, they are of course positive, but then if they're very small, there is a heavy step response. That is to say, it can with a very sensitive region of on and off. So they can behave as an on and off switches, say because of their high sensitivity in that region. But for that, if you take very large values of j1 and j2 above 1, let's just take 1, then you'd see that they do not they still behave as have the sigmoidal behavior, but they're not that sensitive, they're not ultra sensitive. So that means our there are requirements for our j1 and j2 values. So we have j1 j2, I'm sorry, for on off switch behavior, right? That is the essentially the conditions for the system to behave as an on off switch. So you can on Desmos you can do this and play around with different values of j1 j2, or for other for that matter other variables as well. And you can try to find out different behaviors of you see how they quickly and how fast they change with small changes in j1 j2 values, right? So that would be an exercise for you. Next, move on to the next question, which is ninth. A ligand binds to a receptor to form a ligand receptor complex. What is the unit of affinity of the ligand for the receptor? So let's say L plus R, LR as a complex, right? Ligand receptor complex. So they are saying we are asking for unit of affinity. So how do you define affinity for ligand receptor complexes? Affinity measure is the KD, the dissociation constant. So how do you define KD? KD is defined as 1 by the K equilibrium. So here it would be this, right? So assuming that that's only one ligand and one receptor interaction, that is not multiple ligands to a receptor or kind of interaction, we write this equation. So here, so what is the units of this? So we have molar times molar on the molar square on the numerator and molar on the denominator. So essentially, molar is the units of affinity or the dissociation constant we have here, right? Next, the 10th one. We mixed the ligand with its cognate receptor in the solution phase. After 12 hours of incubation, we estimated the amount of free ligand and free receptor in the solution. It was observed that free ligand and receptor concentrations were 1 micromolar and 10 micromolar respectively. The dissociation constant for this interaction is 10 per minus 8 molar. Calculate the concentration of ligand receptor complex form. It's essentially we are using the same equation. KD value is given as 10 power minus 8 molar. L, which is the free ligand, is given as 1 micromolar, and free receptor concentration is given as 10 micromolar. And they're just asking us to find LR, that is the complex concentration. It's just a matter of substituting these values over there. So we have LR equal to L times R by KD. So we have 10 minus 6 times 10 power into 10 power minus 6 by 10 power minus 8. That would be 1 millimolar, right? So that would be the concentration of the complex, ligand receptor complex. Next, 11th question, we have a ligand L binds to a bivalent receptor R sequentially. Eventually, the receptor gets phosphorylated, shown by the red box. The phosphorylation and dephosphorylation follow Michaelis-Menten kinetics. Consider P and E as the total concentrations of kinase and phosphatase. Which of the following is the correct ODE for C2? For they're asking for C2. So I'll just write down here. I'll just write the letters. KC1, KC2, KM2 and C3. So they're asking ODE for C2. So considering C1 to C2, forward rate would be equal to K1 C1 and reverse rate would be equal to K2 C2, right? And consider C2 to C3. Oh, I think I just made a mistake. Sorry. This part we'll just revisit. This is the mistake, but we'll revisit this part at the end. I'll just first write the forward rate here. Forward rate would be equal to um, uh, KC1 PC2 by KM1 plus C2. And similarly, reverse rate would be given by KC1 P C3 by KM1. Uh, I'm sorry, KC2 and KM2 uh, plus C3 plus C3. Okay, so here the question is so here we have C2 as in this particular form, right? So if C2 to C1 transition, either of these two ligands can leave and they are completely independent, right? So we have, I mean, we can write the K1 C2 equation for this only this ligand as well as for only this ligand. That means independently they'll add up. So we have instead of uh, K2 C2, we'll have, let's just take this as K2 dash, we'll have 2 K2 C2, or that is to say K2 dash equal to 2 K2, right? Since there are two ligands which can, leave the complex independently, we'll have, they both add up and it becomes twice K2, right? So we have dC by dt finally equal to the forward rate K1 C1. And for considering the second part, we need to consider the reverse rate as the positive direction, since here forward rate would be uh, a negative for C. that is C is getting sequestered, so it would be negative. Here it would be positive for C, since the C is getting C2 is getting formed here from C from C3. Here C2 is getting formed, so we have positive. So we have K1 C1 plus KC2 KC2 PC3 by KM2 plus C3 minus KC1 PC2 by KM1 plus C2 minus 2 K2 C2, right? So our answer would be the option C, since that's the correct equation. Yeah. And then coming to the last question, the 12th one. So we have a transcription factor T binds to different promoter elements PB1, PB2, PB3, and PB4. The dissociation constants of T are A1, A2, A3, and A4. KD are given by A1, A2, A3, and A4 respectively for PB1, PB2, PB3, and PB4. Okay. Um, and they have also given A1 greater than A2 greater than A3 greater than A4. We use Hill's function to capture the activation dynamics of these promoter systems by T. The Hill constants are given as Hill constants are given as K1, K2, K3, and K4. So now they're asking us to find kind of the order for K1s. So we have this from this particular what do you say uh, relation, we have dissociation constant relation, dissociation constants of uh, A1 greater than A2 greater than A3 greater than A4. Now higher dissociation, higher KD would imply less affinity, right? So we have an opposite kind of rule for the affinities of these four sites for promoter elements. So affinity, if we want to order, that would be the reverse order. So A1 less than A2 less than A3 less than A4, right? So the fourth promoter element has the most affinity among the four for the transcription factor to bind. And coming to the Hill's coefficient, Hill's constant, Hill constant is the half max value, right? Sorry, the uh, value for which half max uh, is obtained. Of final expression is obtained, right? So since we have the order of affinities, uh, and high affinity promoter, if let's say the promoter has very high affinity, then even at low transcription factor concentration, it would get saturated. That is, even if the transcription factor is low, they would definitely go towards that particular promoter site and bind. So the half maximal value for this hill for that particular promoter would be less. So even at less concentration of transcription factor, that is to say, it is binding is gets saturated. So we have Hill constant inverse proportionality. to the affinity, which implies we have K1 greater than K2 greater than K3 greater than K4. Right, from which what are the options? We have I'm sorry, this is 4. Just a second. Mm. So we have option C, right? Option C is K3 greater than K4. Yeah. So yeah, that is with the session, all the questions. Let me know if you have any doubts or clarifications you require. If not, we can end the session.
So could you just explain the 11th question once again?
11th, is it? Okay.
Yes.
Uh, yeah. So 11th, did you understand what what is the question they've asked, right? They've asked us to write the ODE equation for how C2, the complex C2 is changing, right? So now for every reaction, that is every forward and backward the arrows, we have a forward rate and an inverse rate, reverse rate, right? I mean, given that's an irreversible reaction. So if you consider the since we only require C2, you can forget about the transitions from L plus R to C1, since we are only we'll write only in terms of C1, right? You can forget about the L plus R converting into C1 unless you want to expand on it and then write C2 in terms of L and R. You don't require that. So now if you first consider the transition from C1 to C1 to C2, right? We have a forward rate and a reverse rate. Forward rate would be K1 C1, which is straightforward, right? Now, since C1, the structure is this way. One of the binding sites is already occupied. There is only one for occupation. Now C1 to C2, there is only option for one ligand to come and bind here. That is the only option which is there. So it's straightforward K1 C1. But for C2, there are already two binding sites occupied, and out of two, I mean, either could be possible. It could be either this or this. It could be either this or this. Both of them are possible. So you have to double the rate. So K2 is the rate for reverse reaction from C2, that is reverse rate for unbinding of one ligand. So since there are
Sorry,
two
once
possible,
again, how will do for the K2?
no, see, K2 is just for simple reverse reaction, right? Rate of reverse reaction,
Why we are
rate
doubling
constant.
it? Okay,
Yeah,
huh.
so we are doubling it because there are two binding sites occupied, and both of them can leave, right? From C2, you see the structure of C2, right? There are two binding sites occupied by the ligands. Two ligands are there for C2. So it is possible for any of the ligand to leave. The rate constant for one ligand to leave the binding site is K2. Do you get that?
Yeah, got it.
So since I mean one binding, I mean for bindings for only if you're looking at only one particular binding site, that is forget about this. You're looking at only this. Then for this the rate is K2. But also you have other possibility, which is this. For this also K2. That's why you're trying to double.
Okay, yes, got it.
Okay. Yeah. Cool. Then, if there are no other doubts, I'll end the session. You can always put up questions on the forum where if you require any clarifications. Then I'll just stop the recording right now.